All right, so let's start then. It's a big pleasure to have Lyuben Lichev at our seminar today from the Technical University of Vienna. And so Lyuben is a big young expert in probabilistic combinatorics. So please enjoy his talk about the power of choice, a geometric perspective.
Thanks, Maxim. So thank you very much for inviting me. So everything that I'm going to say is based on a joint work with David Ignasiak, who is a promising PhD student in TU Vienna. So the plan of the presentation will be more or less the following. So I'm going to introduce the topic of random geometric graphs and the power of choice paradigm. We're going to cook up a model that combines these two notions. So we're going to consider geometric power of choice, and then we're going to see some of the things we did with David. So maybe let's start without further ado. So in this talk, xn, this will be a vector x1 up to xn of IID random variables, which will be distributed uniformly in the d-dimensional cube 0, 1 to the d. So here I'm talking about the continuous cube, but not the discrete one. And we're going to consider finite dimension, d at least 2. And actually, for the sake of the presentation, I'm only going to tell you things about the planar case. So about the square 0, 1 by 0, 1. So we have these endpoints we throw inside, and these will be the vertices of the so-called random geometric graph with parameter r. So what is this beast? Its vertices are the points that we just sampled in the unit square, and the edges will go between points xi and xj, which land at distance at most r from each other. And as for many random graph models, here as well, most interesting phenomena happen when the graph is sparse, meaning that the number of edges is much smaller than the number of vertex pairs. So in what we're going to look at, the most common regime will be that the radius tends to 0. So as in many random graph models, one can study various graph properties like connectivity, the existence of Hamilton cycle, etc. These are studied usually asymptotically, meaning that for us the number of points will tend to infinity. In GNP, usually the size of the graph tends to infinity, etc. So that's a very common theme in random graph theory, let's say. We don't look at properties for constant size systems, but for like large systems. So this is how the random geometric graph looks like in the very beginning. So here the radius is 0, meaning that we have sampled endpoints, and all of them are isolated vertices of the graph. Then when we increase the radius a little bit, we see these components appear. So currently we are in the subcritical regime, meaning that there are some components which look a bit large, but in reality, like all of them are much smaller than the size of the graph. And then at some point, when we increase the radius a little bit more, we start seeing the so-called giant component. So this is a component which takes a constant proportion of all vertices in the graph. So in particular here I made it a little bit more visible. And of course, some vertices remain outside of the giant component. So in small components, which resemble a little bit the subcritical phase. And so when we increase the radius more, at some point the graph actually becomes connected, so around the so-called connectivity threshold. And the usual thing that happens is that just before connectivity, there is one single vertex which is separated from everything else, and everything except for this vertex forms actually a single connected component. So in this case, there is this red vertex, which is maximally far from all other vertices, and it is the last one to be actually merged in the giant component. So that's a common theme also in random graphs. So one of the most important topics in random graphs and in probabilistic combinatorics in general is the study of thresholds, and in particular sharp thresholds of certain properties. So what do I mean is that we take some monotone increasing property of graphs. So monotone increasing here would mean that if certain graph A has it, and then certain graph B contains A, then B also has the property. So if you add edges, then this property remains true. And so for such a property Q, you can define the so-called heating time for it. And in our case, when we add the points one by one, this will be when we, in this case, we're going to increase the radius continuously. So we start with 0 radius. As we saw before, this gives an isolated vertices, and then we increase the radius continuously. So at some point, our property becomes satisfied, and this is the so-called heating time for this property. Recall that, so this vertex set xn here, it will be fixed for the time being. So we are throwing the points in the cube or in the square, in our case. Then we fix these points, and then we start increasing the radius. And the heating time is the smallest r for which this property is satisfied. Okay, so what is then a sharp threshold for a property? Well, in many cases, it turns out that there is some special value of the radius r, such that if we are slightly below this value, say at 1 minus epsilon times r, then the probability that the property Q of our graph is satisfied tends to 0 when the graph is large. And then if we actually give ourselves a bit longer radius, so at 1 plus epsilon times r, then suddenly our property becomes very typical for the random graph. So the fact that this small change of a factor of 1 plus a little bit makes the property from not being satisfied with high probability to being satisfied with high probability. This is when we say that this property exhibits a sharp threshold, and R is respectively the value of this threshold. Okay, so what properties could be of interest? Well, one of them is, the property that the graph has minimum degree k. Another one is, for example, the property when the graph is k connected. So k connectivity here means that essentially for every if you take any pair of vertices, then deleting any k minus 1 vertices from the rest, you actually don't disconnect your initial 2 vertices. And there are also more global definitions. Okay, so in particular, one connectivity is just the fact that between any two vertices, there is a path in your graph. Okay. So another very classic property is the fact that the graph is Hamiltonian, meaning that it contains a cycle which goes through each of its vertices exactly once. And so these are three of the classical properties. Of course, people have studied a lot more, but if we want to stay with the basics for the moment, let me mention that so the fact that the first two heating times, so MK and TK, so actually the corresponding properties exhibit sharp thresholds, and in dimension 2, Penrose a lot of years ago identified this threshold. And a bit later, it was established by three other authors that Hamiltonicity is also a property that exhibits sharp thresholds for a random geometric graph. And this sharp threshold is actually exactly the same as the one for for minimum degree 1 or k, and also for k connectivity and for any constant k.
Sorry, Lyuben,
So,
may I ask something?
sure.
So this minimum degree k, it's not actually increasing property, not even decreasing, right?
Like if you increase the
Or you mean,
radius,
or
it
you mean
means,
minimum degree at least k, or what the?
yeah, minimum degree at least k, sorry. Sure.
Uh,
The minimum degree at least k, then this is increasing. Thanks. Um, all right. So here I mentioned these three properties just to keep them in mind. So we saw that they have the same sharp threshold, but one could decide to actually go further and to study finer differences between these properties. And it's actually Penrose proved in the same work that he showed sharp threshold, he actually showed something much stronger. So it turns out that of course, having minimum degree at least k is necessary for k connectivity, because otherwise, well, if you have a vertex with degree smaller than k, and you take someone else in the graph, of course, deleting this neighborhood here will disconnect the initial vertex and the final vertex. So the graph is not k connected. And this minimum degree at least k property is necessary, but it turns out that typically it is also sufficient, in the sense that the heating time for k connectivity and the heating time for minimum degree k actually coincide with high probability for every fixed value of k. Okay, so one could wonder, what about Hamiltonicity? Well, if you're Hamiltonian, then you need to have minimum degree 2, and you also need to be 2 connected, because a cycle on n vertices is, well, a cycle itself is a 2 connected graph. So a bit later, well, 8 years later, two groups of researchers have proved that actually the probability that the heating time for Hamiltonicity, the random geometric graph, and the heating time of minimum degree at least 2, these also coincide with high probability. So at the moment when your last vertex of degree 0 or 1 disappears, then suddenly you have a cycle which contains all of your vertices.
I mean, this is the same Mueller in both teams.
Yes, okay, maybe let me, this is the same Mueller in both teams. And in the two papers, they simultaneously claim that these works are independent. So I researched a little bit, so asked Michał Krivelevich what he thinks about it, and he actually said that he didn't notice that this was actually in both papers. So I didn't go to the bottom of the story, but yeah, there is this striking phenomenon of two papers who have a common author and who are claimed to be independent. I can't say more, so maybe we should ask Tobias Müller at some point.
I mean, it's fine, right? Independence for clicks that overlap by one vertex, as soon as they do not overlap by two vertices.
If you apply vertex percolation, not clear. Okay, anyways, yeah, this is a good remark. Let's say that I avoided asking more questions to Michael, but probably I should have. I don't know. All right. So yeah, so this is the end of the presentation for random geometric graphs, or maybe the basics in random geometric graphs. If you have any questions, please ask now.
No, I have maybe simple question,
Sure.
remark. I don't know. You say that graph became connected uh, and so on when last vertex in the picture. And this follows from this theorem if you want rigorously, right? If you want to show it
Yeah,
rigorously, right?
correct. Yes. So that's right. In the particular case of k equal to 1, at the point when your last isolated vertex disappears, you become connected and remain connected. That's completely true. Thanks. Okay. So now it's time to go to the other main topic of this talk, namely the power of choice paradigm. So initially it had nothing to do with random graphs. So the idea comes from load balancing. So you should imagine that you have n bins, and then in these n bins you start throwing in bows in a way that at every step you take one bow and then you throw it in a random bin. Okay. And then you do this n times. So n is the number of bins and n is the number of bows. And then you ask, well, if you do this, what is the maximum number of bows you have in a single bin? And for this process, it's not hard to prove that this number is about log n. And of course, you can find the constant in front and everything. But Mitzenmacher had this idea that, okay, what happens if you don't throw one bow in a random bin, but you're given two bows, you throw both of them in independent bins, and then you need to take one out. So essentially, only one of the bows lands in the corresponding bin, but you have the choice which one. And by doing this, it turns out that after you make n steps of this process, then the maximum load in a single bin actually goes down to log n. And if you increase the number of choices to 3, 4, 5, 6, etc., any constant number will only change the constant in front of the log n, but the real drastic change happens between 1 and 2. So the setting without having a choice and the setting when you have two choices for which bow to leave. Okay.
Do we try to minimize the maximum number of balls when we choose?
That's right. So you can choose your strategy, and the natural strategy here is, of course, to throw in the bow in the smaller bin which is proposed. So you throw in two bows. So one of them goes in a bin which is fuller than the other one, and then these are the new bows. And then, of course, you're going to choose this one, and this one you're going to revoke. And it turns out that by applying this strategy, you can reduce the maximum load from log n to log n. Of course, you can try different strategies, but so as it turns out, this is the best one. and this can be formally proved actually. Okay, is it clear?
Yes, thank you.
All right, and so of course this is not a question about graphs; it's a question about Bose-into bins. And then there was Achlioptas in 2001 who asked, well, maybe if we construct a random graph via a process, we can of course add the edges one by one, uniformly at random. But following the two-choice paradigm, there is of course the option to sample every time two random edges, and then we can decide which of these two random edges we want to include in the graph and which we don't want to include in the graph. Of course, this is just a process, and the goal is unclear, and the goal could be like very different depending on the property we want to reach for this graph. So there is actually a rich line of research that this process generated. So here is again the description of the process. At every step you're given two edges, and then you choose which one of them to construct. And you can have different goals. You can want to accelerate some property like the appearance of a giant component, or connectivity, or the existence of a perfect matching, small subgraphs, etc. You can take your favorite graph property and you can study it in this process. Or you can, of course, want to delay your property. Okay, and why was Achlioptas' process so influential? In their initial paper, they observed for a slight variation of this process that if you add the edge which minimizes the product of the two components of its endpoints, so again, so you're given these two edges here, and then these vertices are in some components. And then you can create this rule that you're looking at, maybe this is C1, C2, C1 prime, C2 prime, and you're looking at the product of C1, C2, and if this is larger than C1 prime, C2 prime, then you say, okay, I want to actually construct the edge between the pairs of components which have smaller product of their sizes. And this is just a rule, like the goal is unclear, but they actually observed some simulations for this rule for different graph properties, and it appeared that the giant component actually, under this rule, undergoes a discontinuous phase transition. So when your number of vertices is very large, and then you try to simulate this process, it turns out that you have only small components, and then at some point you have a component which has size at least 1% of your vertex set. And they were very surprised because this such a discontinuous phase transition is not known to hold in any model of random graphs. And this has been a major open problem for like probably 10 years until Oliver Jordan and Lutz Warnke actually disproved it. So they showed that the transition is continuous at the critical point where a giant appears. And so the curious thing about this paper is that it appeared in Science. So which, it's a journal for usually physics, biology, chemistry papers, maybe social sciences, but another math paper barely reached this literature. So this is a big exception. Okay, so maybe let's come back to our geometric model. So
Sorry, can you clarify what is continuous and discontinuous transition? What
yes,
is the
of course.
difference?
So you can study a process and you can throw in your edges, right? So maybe let's say that for convenience we'll study the Erdős-Rényi graph process. So you're going to throw in edges randomly one by one on a set of n vertices, okay? And then here you are going to look at the size of the largest component, so C max divided by n. So n is the total number of vertices, and the size of C max is just the number of vertices in the maximal component. And then on the other axis, I'm going to draw t divided by n. So at some point alpha, this will mean that I have made alpha n steps in my process. So in the Erdős-Rényi case, what you're going to see, well, you throw in the edges one by one, and at some point you reach the point 1/2. So below this point, you're going to have that your maximal component has actually logarithmic size. So it's very, very small compared to the size of the graph, the entire graph. And then suddenly at 1/2, something happens, and then you start seeing a giant component. And then, of course, when you increase the number of steps, the size of this giant component, so the proportion of vertices of this giant component converges to 1. And when I say continuous phase transition, I am essentially saying that in this point where the magic happens, so where the phase transition happens, the giant component very close but above 1/2 is still very small. So when you take your parameter 10 to 1/2 from above, the proportion of vertices in the giant component will tend to 0. So this is continuous phase transition, and for essentially all random graph models that we know, the giant component undergoes a continuous phase transition. And in the paper of Achlioptas and collaborators, they said, oh, this actually looks like a model where we have a discontinuous phase transition for the giant, meaning that at the critical point, you suddenly see a positive proportion of the vertices being in your giant component. So something like this, some transition like this, and here this is excluded. And then the paper of Oliver Jordan and Lutz Warnke show that no, this is actually not the case. And this jump that appears in simulations, it comes from the fact that the precision of their simulations was not good enough.
Also, if we start to discuss it in so much details, is it clear that 1/2 is the same?
Yeah, it's not the same. It's a different number.
It's not the same. Okay.
No, it's not the same. Like you can make the giant component appear faster in this case. But at the
Thank
point
you.
where the phase transition happens, actually the growth is very, very abrupt, but it turns out it's still continuous. Okay, so maybe if there are no more questions, let me try to move further. So again, so we introduced this geometric model, so we're going to try to actually stick to it and see if the two-choice paradigm actually makes any sense in this model. So the classic source of randomness in the model of Achlioptas, as I described it, was the edges. So you're given two edges, and you can decide which one of these two edges to include in the graph. But so for us, the edges are decided by some radius, so it's somehow unnatural to choose between two edges. But somehow the bits of randomness that we see in our graph, they're given by the vertices. So the vertices are random, and what we can say is, okay, so let's fix some radius, and let's consider some sequence of random graphs where The nth graph will be obtained by the first n random points in some sequence, where again you connect every two of them which are a distance at most r. And of course you can see this as a process which is a bit analogous to the process, the Shreni process before. Okay, doesn't it work? So in a similar way, you can say, okay, for my fixed R and for some property Q, I can define the heating time of this property Q as the smallest integer n, such that my geometric random graph with n vertices has this property. So you throw in points one by one, and at the nth step, you suddenly see your property Q. And as in the standard setting of the Erdős-Rényi graph, we would like, of course, to study this heating time of different properties, with the difference now that our asymptotic parameter will be the radius. So before, in the classical random geometry graph theory that I showed you, our radius was fixed as a function of n, and then our endpoints were thrown in. They were static. So here we're going to throw the points one by one. We're going to see what happens when the radius tends to 0. So everything that we express will be in terms of this radius and not of the number of vertices. So again, well, how will the process look like? Well, if we want two choices, then we're going to sample these points in pairs. So x to I minus 1 and x to I. And we're going to keep only one of these 2 points. Which one, of course, depends for our goal. So maybe something that I'd like to observe is that we can run this process in 2 different ways. So we can run it in an online fashion, meaning that we don't know what happened, what happens in the future. We just know what happened like before in the past. Or we can run it offline, meaning that we have some sequence of random points. We first expose this degree sequence, so we have complete information about the process. And then once we do this, we can decide for which point from every pair we need for our purposes. And as we're going to see, these 2 settings actually lead to very, very drastic changes.
Lyuben, just a quick question.
Yes, sure.
So this way of defining the process, even before you have the power of choice, that you just add vertices one by one until you hit the property. Well, it seems natural, right? So it probably was also considered in some other papers before introducing the power of choice.
Yeah, so we managed to find exactly one other paper. So that's actually a good point. There is a paper of Tobias Müller and the student of his whose name I don't remember.
But is this for hyperbolic geometry? No.
No, it's about the Euclidean setting. But so they were studying the essentially an analog of the Archioptas question, which was resolved by Riordan and Warnke. So they were trying to analyze how fast you can get a giant component.
Thanks.
Yeah. So yes, this is true. This process existed before. We actually managed to find this paper a little bit after we submitted the first version of our paper. But yeah, it exists. Okay, so maybe one small thing which is actually somewhat important. So for increasing properties, as for example connectivity, where if you add edges to your graph and it was connected before, then it stays connected after. In our version, these are not monotone in the following sense. So you can have a graph which is connected like here, but of course it can have large empty regions, where if you add a point, then this point becomes isolated. So this underlines the difference between adding edges and adding vertices, right? So adding vertices, of course, can destroy some increasing properties. So maybe before studying heating times and sharp thresholds for increasing properties, we need to ask the question, well, actually, once we have the property, do we typically keep it? It's clear that deterministically this is not true, as this picture shows, but probably it happens with high probability. So we managed to formalize this with the idea of probabilistic monotonicity. So what's that? So we said that our radius tends to 0, and then in this asymptotic regime, we sample points one by one. So we say that one property Q is probabilistically monotone if with probability 1, once we hit this property actually remains true forever. So formally, for every n larger than the heating time, the random geometry graph generated by xn and radius r actually has the property Q. And so maybe also another small thing, usually when we say with high probability, we mean with probability which tends to 1 as the number of vertices tends to infinity. So here our asymptotic parameter is the radius, right? So here we'll say that the property holds with high probability if when the radius tends to 0, some event which depends on this radius, its probability tends to 1. So there is this important difference to avoid confusion. Okay, so
But this
now
event, sorry, Lyuben, this event considered for when the number of vertices is exactly tau.
So of course you can have any event that you define.
Or you mean you consider the entire process for a fixed star?
Right, exactly, yeah.
Okay.
So in this case, you don't need to define any heating time. It's a little bit like in usual Erdős-Rényi graphs, right? So you can define some properties which are not related to some heating times or whatever. They just hold with high probability in a dense graph, for example. So here it's the same thing. Okay. So it's time to tell you something about our results. So the first theorem has nothing to do with the power of choice, and it essentially claims that some typical properties, that like usual properties, are probabilistically monotone. So the minimum degree, at least k, property K connectivity, Hamiltonicity, all of them are indeed probabilistically monotone. And except for that, the expected heating time equalities actually hold. So the graph becomes K connected at the first time when it reaches minimum degree at least K. And it becomes Hamiltonian when it reaches minimum degree at least 2. At which point, of course, by the first part, it also becomes 2 connected for the first time. Okay, so this was the setting without choice. Now, what can we say about offline choice? So let me recall. So offline choice process is where you expose your random sequence of vertices in the beginning. So you see the entire sequence, and then you go pair by pair and say, okay, this vertex will be more useful for my purpose than the other one, so I choose this one from every pair of odd vertex, even vertex. So in this case, so what can we say? Well, if we want our graph to be connected, for example, what is like a simple property that we need? Well, if we have some graph and we have two vertices, which at distance r have no other vertex, can the graph be connected to whatever we have outside? Well, of course not, because we have to choose either one of them or the other, but whichever vertex we choose, we're going to form an isolated vertex. So the graph cannot be connected after that. So the minimum condition for connectivity, for example, that we can ask is that for every pair of vertices in our process, at least one of these vertices has a third point, which comes before this pair here, and which can be included in the graph. Okay, and it turns out that this is sufficient, not only for connectivity, but also for K connectivity. So if I give you my infinite sequence of points, and I ask you, well, when do I become K connected, if I have to choose exactly one of them, we can show that we become K connected at the point when no pair of vertices, which is smaller than the heating time, consists of two vertices which have degree less than k both of them. So in particular, for the connectivity property, when k is equal to 1, this will mean exactly what I drew above. So the heating time will be at the point, so the heating time for connectivity will be at the point when all pairs of vertices smaller than my heating time, I have at least I have at least a third point here, which is within reach of one of the two vertices, like one of the two partner vertices. Okay, and then for Hamiltonicity, we have the expected analog. So a graph can be made Hamiltonian at the same heating time as for two connectivity, and this would mean that when you look at the pairs, for every pair, you need to have at least one vertex which sees two other vertices around it. All right. So that's the result. So maybe what does it quantitatively say about the acceleration of the property? Well, these thresholds, if we look at them in the process without choice, we will need to do 2 times more steps in order to be connected, for example, or K connected. But so 2 times more steps would, in the non-choice setting, would actually mean that we need 4 times more vertices. Because at each step in the choice process, we of course choose one of the 2 points. And in the process without choice, we don't have a choice, so we include the point whatever happens. So here, in terms of time, we accelerate the process 2 times, and we need 4 times less points than the usual process. So what about online choice? So when we cannot see the entire sequence of points, but we need to decide only based on the history of the process. So in this case, it turns out that the sharp thresholds in terms of number of points we need to see in the process, they actually coincide. So we cannot obtain a connected graph much earlier, so with much fewer points, than the number of points which are needed for this in the process without choice. So both of these properties of K connectivity and Hamiltonicity, we can accelerate them a little bit, but it's essentially by lower order terms, so it's not that interesting. Okay, so these are the results. Now I'm going to tell you maybe little bits of proof ideas. So first is the simplest setting, the setting without any choice. So here is again the theorem. So each of the properties, minimum degree at least k connectivity, and homotonicity, these are probabilistically monotone. And moreover, the expected heating time inequalities hold with high probability. And to not enter into too much detail, maybe let's look only at the minimum degree 1 property. The ideas would be similar, but technically more involved for the other ones. So how do we show that this property is probabilistically monotone? Well, what should happen? We should prove that once we see a graph where we have no isolated vertices, then we are going to have no isolated vertices ever again. So in particular, this includes the task of describing, well, once we don't have isolated vertices, which are the potential regions where if a vertex lands, it becomes isolated. So this is some kind of dangerous area. So you should think about this picture here, where we have this region here, which if a point lands here, then of course it's going to be isolated. And then in order to prove that our property of not having isolated vertices is probabilistically monotone, what should happen? Well, these regions should disappear. So if a point lands there, then it's bad for us. But typically, we should actually prove that this is not the case. So instead of having point which lands in this region, it's actually much more probable that a point lands very close to this region, but still connects to the rest of the graph. And if this happens, well, this region is not dangerous anymore, in the sense that whatever lands there, it will actually be merged with our giant components, which is, well, with our connected graph, essentially. Okay, so what's the approximate idea of proving this? Well, we need to look close to the heating time of the property of not having isolated vertices. And at this heating time, what do we have? Maybe let me do some additional picture. We have two types of objects. So just a little bit before all isolated vertices disappear, we probably have a constant number of isolated vertices. And we have some small areas where if a vertex lands, then it would be isolated. And then everything else is in the giant connected component. Okay, so when we look at the isolated points, it's somewhat clear what we should do with them. So we should wait for a vertex which lands close to them and automatically merges them to the giant component, which is not far from them. So we're just waiting for another point. So these are somehow the easy abstractions to why we are not yet connected. So the area, which is the dangerous area, so to say, you can prove in a similar way that you can prove in roughly the same way that you have few isolated vertices and you have a small dangerous area. So at some point, both of them, so you're going to have big O of 1 isolated vertices, and your isolated area will be roughly 1 over tau, where tau is essentially your heating time for connectivity. So this is very small area, but although it's very small, it could be super well spread around the square into very, very, very small chunks. So in order to control this area, it turns out that one should do a tessellation of the square with the correct mesh. So as in this picture. So once you do a suitable tessellation of the square, it turns out that this dangerous area would actually be very well controlled, and you have a small number of clusters which it forms in. And around it, you actually have much more. So this is the dark green region. So the dark green region, it turns out to be actually much, much larger than the dangerous area here. And so once we prove that these white clusters here are actually, there is a very small number of them, you just need to have a vertex which, so a small number of vertices actually, which visits the green area and which eats like the entire white dangerous part. And by actually finding the right mesh for the small squares, this is not too hard to do. So that's the proof idea, more or less. Okay, I guess I need to delete this. All right. So this was the setting without choice. So maybe let me proceed to the offline choice setting, where again we see the entire sequence of points, and we want to prove the typical heating time identities. So you're not you become K connected at the point when every partner pair contains one vertex of degree at least K, and you become Hamiltonian essentially when you become two connected. So again, to avoid a lot of technicalities, maybe let me comment only on the connectivity case. So again, this is the case when we want to become connected at the point when we don't have partner pairs which are both isolated. So how does the proof go? Well, in a very briefly, so very rough sketch. Of course, so in order to be connected, one should remove small components which are outside the giant. And there we have no choice. So we remove these small isolated components, and then this requires that some vertices are forced in the graph, but very few of them. And so once we have these very few vertices, which are typically in the giant land, then we are relatively free what to do with the other vertices. So currently we have a giant which is very, very dense. So for example, like here, we have a small number of isolated components, which we need to get rid of. So we get rid of them, just forcing some vertices in this graph. And then this graph is quite dense. So the random graphs are usually quite clustered. So this means that around the typical point, you have many neighbors. And this property allows us to sparsify a little bit in order to roughly keep the geometry of the graph without losing its connectivity property. And so, oops. So I realize this is probably too fast, and I have a little bit of time. So maybe let me tell you in a bit more detail how we deal with the vertices outside of the small ones. So we have. So how should you think about the random geometry graph in this regime? Well, you have so a typical vertex has a logarithmic number of points, which means that the graph is very dense, like almost everywhere. And okay, maybe let me draw a little bit. So the graph is quite dense. Okay, and then in these windows where it's actually not that dense, so you have these small islands here, which could be empty, which could contain some component which is disconnected from the rest, and which could contain a component which is relatively dense, a little bit large, but also very weakly connected with the rest of the graph. So in these pieces that I crossed many times, think of these as essentially points which have like at least log n over 10 neighbors. So what do we need to do? Well, we need to destroy, maybe let me draw them in red. We need to destroy these small components here, which are in the islands which are not visited. So these need to go. And typically for the large, like a very large number of these vertices have their partner pairs in the giant. Okay, so maybe let me go in a dense core, in a sort of dense core. So the blue guys are partners of vertices in the red components. Okay, so if these are all in the very dense core, we would be fine. Of course, there could be some point which is partner of a point in a small component, which lands in some of these components which are connected to the giant, but somehow very sparsely via a very long path. So it is essentially this setting that we need to be a bit careful with. So this setting here, maybe let me draw it in blue. So this setting here is somewhat the boogeyman for us. What happens if we are forced to take a point in some component which is inside the giant? So it's a vertex which is inside the giant, but is somehow very sparsely connected to the giant via a path, well, here of length 2. But so in particular, this vertex here, I say that it needs to be included to preserve connectivity. Okay, so the point here is that if you delete all small components, most of the vertices will be in the dense giant, and such small components like here, which are very weakly which are in the giant but are very weakly connected in the giant, you can force at most one blue point in them. So in everything which is like not 100 connected within the giant, in any such small set of vertices, you can say I have a unique point which I am forced to use here. And because you have a unique point, and these clusters are usually quite large, then you can organize the graph around you in order to say, okay, if I need to have this point, I actually need to add a path from this point to some dense core in the giant. And you actually need to do this a relatively small number of times, meaning that the partner pairs of the red points almost exclusively are in some dense core here. So the blue points that I drawn, they're almost exclusively in some very dense core. And the problems that you have to fix for connectivity basically reduce to a logarithmic number of such dangerous weakly connected pieces of the giant. And so once you deal with them, you're fine. This is what I want to say about connectivity. I won't go into details for k-connectivity and homotonicity. Essentially, so maybe one sentence, the proof there is very similar, but we have to do a much more robust case analysis for these small components. Okay, so that was the offline to choice, which was probably the most painful part of this presentation. So for the end, I left the online choice, the online choice setting, where I cannot promise you any hitting times. So I can only promise you that the process is actually cannot accelerate much the presence of connectivity, homogeneity, etc. So here I want to concentrate once again on connectivity and give you a very brief idea why we need to see roughly the same number of points as the process without choice in order to be connected. Okay, so everything I'm going to say will be contained in this picture. So I'm looking at one connectivity, so connectivity. And so what was my process without choice doing? It was throwing in points one by one, right? And then at some point I hit connectivity, and we saw that with high probability we remain connected. Okay, very well. So let's see what happens a little bit before. So a little bit before connectivity, we had a large number of isolated vertices, and these are my blue points here. So the points which have a blue bow around. Okay, so what about them? I want to stop at a moment when my blue points, their number is much, much larger than logarithm of the number of vertices, which is logarithm of the hitting time for connectivity. And so, okay, maybe let me mention here. So the hitting time for a giant component, if this is n, then the hitting time for connectivity, exactly as in the Erdős-Rényi setting, this will be roughly around n log n. So I need to have logarithmic degree in the number of vertices in order to become connected. And here I'm telling you, well, look at time of the process where the blue vertices, so the isolated vertices, are much, much larger than log n. And we're still close to T connectivity. Okay, what does this mean? When I just look at my graph, and I look at my isolated vertices, I see they're isolated, but if I don't recall the indices of my points, I don't know if my isolated vertices arrived early or late. They may have been the first vertex that entered the graph. They may have been the last vertex. I don't know that. I can just see that there is nobody around them. Okay, but if their number is much larger than log n, and then I did not have a giant before n steps, then it means that typically many of them actually appeared much before I had a giant. So many of them appeared when most of my vertices were isolated. And okay, let's say that 3 of them did. So I will draw edges for the partner pairs. So let's say that this guy here, this guy, and this guy, they appeared at the point when both them and their partners were isolated. So they were not seeing any vertices around. What does this mean? This means that, well, when I had this pair, let's say that this pair comes first, I may have chosen the red point, like the point with the red bow, but it would have changed nothing at this point. So I only know the history of the process. So the fact that this guy remains isolated for long, or this guy remains isolated for long, I cannot know it at this point. So I have probability 1/2 to make a mistake. So probability 1/2 for mistake. And the mistake here would be to choose the point which will remain isolated for longer, actually, so close to the connectivity threshold. And okay, so for one pair, I have probability 1/2 for mistake, but this is actually true for every pair which arrived so that both vertices were isolated. So 1/2 for mistake here and 1/2 for mistake here.
Sorry, Lyuben, this I missed. When you define this online choice and when you don't have a choice, you just do the choices probability 1/2.
Yeah, so the point is more that when you have you have a choice the whole time.
I mean, when it's the same.
Yes, when it's the same, then of course you can choose your point with probability 1/2. But my point is that however you choose it, according to whichever rule which is measurable in terms of your history, you cannot predict which point is going to be isolated for longer.
So whatever function you take of your history, you're saying that the probability is 1/2.
Yes, because so if you're going to be isolated in the future or not, it only depends on the future points. And these future points, they carry some fresh randomness. So whichever algorithm you use in order to choose a pair of vertices which are both isolated at this current point, then you have probability 1/2 to choose the vertex which will remain isolated for longer.
When you say that it remains isolated, do you mean that no other vertices, both chosen and unchosen, will appear in the area?
So to remain isolated, I mean that of course you have other vertices which come, right? So they're thrown in your space. And at some point, one of these two points above that I saw, at some point, some of them stops being isolated. So there is some vertex in the future that appears close to one of them.
It depends on whether you choose this future vertex or skip it and choose.
Yes, right. But in particular, let's say that in the best case for you, if it's close to a vertex which is isolated, you're going to take it.
Okay.
But of course, so I drew this point here in the red circle, but it may come here with the same probability. It may come in the blue circle. But I have no way to know this in advance, right? So I have some fresh randomness coming from the points in the future. I don't know if the blue bow will contain another point in the future faster than the red bow or vice versa. So this blue vertex, so this vertex here, it remained isolated for long, but at the point when I chose it, then of course the red vertex had the same probability to remain isolated for very long. So if I had to choose one of the two vertices, I must have chosen this vertex that remained isolated for long with probability 1/2. And then, of course, this is true for every pair which arrives so that both vertices are isolated. And if you have many of them, then this means that you do a mistake with probability 1/2 for each of them. Right? So if the number of blue pairs which arrived much before I had a nice giant component, then this means that I did mistake with probability 1/2 for the first one, for the second one, for the third one, etc. Well, if I have many such pairs, then with high probability, I will have chosen one of the vertices that remains isolated for so long. And this means that I cannot accelerate connectivity by much because isolated vertices will still be there close to the threshold. And in particular, when the isolated vertices are much more than logarithm of n. Okay, so maybe is the strategy more or less a bit more clear?
So can we accelerate it roughly 2 times because we reveal 2 times more vertices. So if we have an isolated vertex around threshold moment, the probability that we get a vertex, one of two vertices near it, is 2 times more than the probability that we have one random vertex near it. Is it true?
Maybe say again. I'm not sure I understood.
So, assume we have very few remaining isolated vertices.
Yes.
And we are around this threshold moment.
Yes.
So, in the case when we have no choice, we have 2 times less probability in each step to make this vertex not isolated than when we choose than when we have two variants. Is it true?
I see. So I think that, yes, so that's a good point. So when you're late in the process, say a vertex which appears after a million times n steps, it is actually much less likely to be isolated than in the very beginning. So essentially, the vertices which remain isolated for long, many of them arrive very, very early in the process. So essentially, what we're trying to exploit here is that if you have a large number of isolated vertices, then actually many of them arrived quite early in the process. Of course, if you are very late in the process, your graph is very dense. So it's very improbable that a new isolated vertex will appear. But it's not so improbable that the many vertices which were isolated from the beginning, they actually remain isolated for long. I don't know if it answers the question.
Think no. Well, the point is that when we have an isolated vertex already that is isolated from the beginning, then we have in the same number of steps we have 2 times more opportunities to connect it because we thrown 2 times more vertices. Does it mean that we have 2 times acceleration?
I see.
Not?
So it doesn't for the following reason. So when you have few isolated vertices, then you have parts which are like everything outside of them is actually quite dense, right? So this is a very dense area. And the point is that when I have a point which lands in some of these bows, so it makes a vertex, maybe let me draw in the blue ones, when some vertex arrives in a blue bow, then its partner, it's very probable that it lands somewhere in the already dense core. So it would have been true, what you say, that you destroy your isolated vertices with speed which is 2 times higher, if the typical scenario was that when I destroy one of the balls, then somehow, I guess you look at a pair of vertices and you want this pair of vertices to destroy two isolated vertices at the same time. But late in the process, what it happens is that when one isolated vertex is destroyed, then the other partner vertex in this pair is actually in the giant. So it is useless for you. You can't use it. But at the same time, there is this one vertex in the pair which is useful for you. So otherwise said, in the online process and in the process without choice, the speed with destroying isolated vertices in the end is the same. essentially. Because in every pair, only one of the two vertices is useful for you. The other one is somewhere in the giant, and you don't care about it. Is it okay?
And how do we measure the critical moment? Is it the number of vertices or the number of steps?
So the
two times difference.
Maybe let me say T connectivity for online choice. This will be the minimum n, such that okay, maybe let me define it for the non-choice process. This is the minimum n, such that the graph on n vertices with radius r is connected. Okay, and then the threshold for connectivity in the online choice process is the minimum, let's say 2n, such that there exists a strategy. There exists a strategy, meaning that, so this is some subset S in 2n, which so it's a subset, online chosen subset, if it makes sense. So in order to choose the next element of the subset, I need only to look at the previous ones. So I don't have information from the future. So measurable in terms of the process. Such that the graph on this set S and radius R is connected.
Okay, I see. I assumed that there will be n instead of 2n, and that's why I thought that
I see.
there should be 2 times difference.
So yes, so in terms of number of points, there are 2 times fewer points that you use. But in terms of number of points that you see in the process, they're essentially the same. Yeah, so this is more or less what I wanted to tell you this time. And thank you for your attention. And of course, if there are any additional questions, happy to take them.
Yeah, thank you very much, Lyuben. Very interesting. Any questions?
It's a general question. In this talk, you said about the situation when we try to accelerate the process, and what if we try to keep graph unconnected as long as we can? Is it studied?
Yes. So I don't think it has been studied, but it's a somewhat easier setting, because you can say, okay, so if I fix the square and let's say I sample my first point, then you can say, okay, so I have some neighborhood of this point, and you can require to sample if a pair lands, both points lands outside of the bow, then it doesn't matter which you sample. If some of the points lands inside of the bow, then you sample the other one. And with this strategy, you can keep this vertex here isolated for a very long time. And so I'm not 100% certain, but I would say that it's very probable that like the longest time you can keep your graph disconnected would be just to sample your first vertex and to keep it isolated for as long as possible. But I haven't thought about this question, and I don't think it has been studied.
Lyuben, there are at least two things that I missed during your talk. So first, is there a difference? So first of all, when you didn't have a choice, and so when there was the first part of your talk, and then you explained the behavior heating time for Hamiltonistic connectivity and so on and so forth, you have similar behavior as in GNP.
Yes.
What about the power? What about when you have a choice? Is there some crucial difference with GNP?
So I don't quite remember the paper which studied these things in GNP. Let me think a bit about this. Somehow so I can't quite recall the results for GNP in this direction, but something which is very specific for the geometric setting is that you, of course, in GNP number of vertices is fixed, and if you sample edges, then if you take an increasing property, then once it's satisfied, it remains satisfied. So this probabilistic monotonicity will be kind of irrelevant there.
No, that's true, of course.
And in connection to this, the fact that you need to control some of these some dangerous area, as we saw in these pictures, so it's somehow related. So you need most of our effort goes into trying to control the probability that someone lands in this dangerous area and becomes either isolated for connectivity or has degree at most k-1 for k connectivity. So somehow the difficulty is in a very different place, I would say.
But in terms of results, if you again compare moments when the minimum degree is k and when there's k connectivity,
I'd say that it should be essentially the same phenomenology.
Mm. Also, in the beginning, you started from any dimension, but then, as far as I understand, all your story was about dimension 2. Is it all generalized to higher dimensions?
Yes, I just did dimension 2 because we can have nice pictures and.
But all results are true in any.
In terms of results and proofs, yes, the increasing the dimension doesn't bring like additional complications, and the reason for this is that we are looking at very dense regime. So also in I would say other percolation models which are not on a fixed lattice, if you look at properties where the expected degree is already much larger than 1, the dimension is not of such importance. It starts kicking in if you look around the giant component. So actually, there are these famous questions in percolation that ask if you have continuous, discontinuous phase transition in dimension 3, 4, 5. But yeah, here we don't have these problems because everything is quite dense. So we use some renormalization tricks, which essentially translate what we are doing to very, very, very supercritical percolation on ZD. But because it's very, very, very supercritical, things are actually easy to study.
I see, but if you change the geometries, then your arguments will they still work, or?
In which sense? You mean in
For
hyperbolic?
example, with hyperbolic geometry.
Oof. What we're doing is quite robust, but like first of all, it would be like much more technical computations. I'm guessing that we don't use something very specific for Euclidean case, but yeah, we haven't tried.
I see. Thanks.
Sure.
Any other questions?
Thank you. Thank you for the talk. It was very interesting. So, do you study or do you have plan to study some more complicated geometrical things like spanning trees, Steiner trees and such setting?
There is.
It's much more complicated because just simply remark it heavily depend on dimensions, constants are unknown and so on only.
When you say this, you mean for the like the simpler setting without choice, I suppose.
No, it is complicated even without choice.
Yes, yes.
So, but so the question, so I understand that it's not generalizable in an easy way. So the question is, are you study this or heard on this or think on this or not?
Yeah, I'm thinking about different questions on random point sets. Actually the statistics of the minimum spanning tree in random geometric graphs and on random point sets in general, when you take weights to be proportional to the distance between points. Yes, I think that indeed this object hasn't been studied enough. So they don't know precisely its diameter. They don't know a scaling limit. I think that finding a scaling limit for this is an open problem. Yeah, these are all like super interesting questions, I think.
So again, you take, so it's about scaling limit for the minimum spanning tree in terms of
Yeah,
its, how do you define
right.
weights again?
So you take endpoints, and then the length of the Euclidean length of an edge is its weight.
So same model, you have just random
Yeah,
points on the
right.
plane, say.
And then you construct the minimum spanning tree on these endpoints. And then you ask, well, if you renormalize
Sure.
by the diameter,
So you're saying
what
even
does it
in dimension 2 is not known.
I think that in any dimension larger than
Yes.
one.
The constants are very complicated there because it appears some stuff like kissing numbers, so on. It's something like this.
Yeah, could be. But yeah, it's definitely a question worth studying. Maybe another open question, which I actually very much like, is you can take a random geometry graph and then you can start increasing the radius. And we know that if you at the point when you start seeing all possible trees as a spanning tree, so the universality for spanning trees of bounded degree, it happens when your radius is something like 1 over um, what should it be? I think 1 over log n. Maybe I'm lying for some power, and somehow the boogeyman here is, for example, the binary tree. The binary tree has diameter of order log n. And if you want to see it inside your graph, then of course you need to connect the 2 points which are very close to the corners. So you need to have a logarithmic path between them. But okay, so the threshold there is known, it's roughly 1 over log. But what about finding almost every tree? Finding almost every tree should not require diameter of order log n, because the diameter of a typical tree is of order n to the 1/2. And then it actually means that we can probably do much smaller jumps. But we don't know. So we don't know. We know that the threshold should be very different because we have like a polynomial improvement on this 1 over log n, but we cannot nail it down to, for example, the connectivity threshold if it's the right one, or even logarithmic factors.
When you say almost every tree, you do not upper bound its degree.
You don't have to, because you have connectivity necessarily. And when you're connected, you are for the degree for the log n. And I think this is roughly your maximum degree there.
I see.
So yeah, there are very, very interesting questions in this direction.
Okay, so if there are no more questions, thanks again, Lyuben, for the great talk. It was a pleasure.